Hello everyone, this is our lecture 6 and we are going to talk about non-parametric models, about sieves and the natural extension from the linear models that we have been discussing so far. Okay? So I'm going to give you a general overview, then we are going to look at linear sieves and then move into non-linear sieves that will be the basis for the upcoming machine learning methods that we are going to study during the next lectures. As for references, there are one very good paper on Econometrica, but it's kind of dense in terms of math and theory. There's a very nice survey paper on the Handbook of Econometrics by Chen-Hong Chen, and also in our textbook, Hasty, Tibshran, and Friedman, in chapter 5, there is some discussion on the topic. Okay, so let's look into the semi-parametric sieve estimation. So let's recall that let's suppose that we want to estimate the condition expectation of y on x, and we call this condition expectation a function h, which is unknown of x. Okay? And our goal is to estimate this function h of x, which belongs to a function space calligraphic h. It's a very general space because we are not imposing any restrictions on the form of h. Okay? And x is a vector of p explanatory variables. Okay? In most of these lectures we are going to assume that p is fixed, so we are in a setup where p is less than t. Further in the next lectures we are going to kind of generalize that to allow for big p, so really large dimensional setups. Okay? The problem is that this problem is unfeasible when this function space is infinite dimensional, because we want to estimate h hat as the argument that minimizes the sum of squares errors, the sum of squared errors, but we have to search over all the h calligraphic h space. Okay. The problem is that we don't have a feasible technique, an efficient technique to search over all h. Okay? What are the examples of the function spaces? We can consider the spaces of continuous functions. We can consider the space of twice continuously differentiable functions, or you can go in more general spaces and look at the space of Borel measurable functions. Okay? Of course, we can always restrict the space. We can, for instance, impose linearity. That's what we have been doing so far. So h will be equal to L. That's the class of linear functions, beta transpose x, and beta belongs to the RP. So that's the space of all linear functions of x. That's a very simple case. L is finite dimensional with dimension p, and we have a solution for that problem. Okay. So what be the solution? What we are going to do? We are going to restrict the class of functions h to a simpler function space. Okay, and basically we are going to search over this finite dimension space HD. Okay, so we have a restricted version of it, so we are kind of imposing restrictions on the functional form of h. Okay, but still we are going to be very flexible in terms of which kind of functions we can approximate. So what's the idea? That the solution is called the method of sieves. So we pick a sequence of finite dimension spaces, HD, d equals to 1, 2, 3, so on and so forth, that converge to calligraphic h. So that we have a sequence of simpler space, but that in the end, when we increase the dimension of this space, we recover the original space that we would like to search over. Okay? And we are going to define an approximation function on this calligraphic HD space that we are going to call lowercase h d of x as a sum, as a weighted sum of simpler functions hj. Okay? We call hj the basis function, okay, or the sieves for the space calligraphic hd, and this function can be fully known, as we are going to see in many examples, or even indexed by a vector of parameters that we will have to estimate. And then we have hj of x will be an h of xt and a vector of parameters theta j. Okay? And the number of basis functions that we have here, look at that depends on the sample size capital T. Okay? As the sample size increases, we want the number of basis functions to increase, because as j grows, we are going to improve our approximation capability of the unknown original function that's our target. Okay? And d is the dimension of the space, and it also depends on the sample size. Okay? And bear in mind that d not necessarily equals to j, because we may have parameters, many parameters inside each function h. Okay? Of course, when there is no parameter theta, then d equals to j. Otherwise, d is larger than j. Okay? So, which kind of simpler functions we can consider? Like polynomials is the simplest approach. So hd will be the space of polynomial functions of x up toward the j, and since the functions here will be fully known, d equals to j. We can have like trigonometric functions, okay, and hd is there's kind of a, sorry, is a typo here, I'm going to correct it. The sieve space defined by sine and cosine functions, okay? Or, as we are going to see further in the course, regression trees and neural networks will also be can be interpreted as this sieve approximation. Okay, so for the moment we are not discussing neither regression trees or neural networks. We are going to look at them a little bit later in the course, but let's look at polynomials and trigonometric functions. Okay, and how do we define the sequence of space hd that should converge to h? Okay, how we select that? There is the fundamental concept that's called about dense sets. Okay, so if we have two sets A and B that belongs to a metric space calligraphic X, we say that A is dense in B if for any epsilon, any positive epsilon that belongs to the real numbers, and X belonging to B, there is an Y belonging to A such that the difference between X and Y in this specific norm on X will be less than epsilon. So we're basically saying that we can make X and Y very very close to each other. So we are approximating these functions. So we want to define like basis functions that will be simpler functions such that we can, as we increase the number of these functions and we look at these combinations that we have here, we want to show that when j of t diverges, this term here gets really close to the original function that we want to approximate, okay, as jt goes to infinite. Okay? So we are improving our capacity to recover the original and unknown nonlinear function that's, in the end of the day, is our target. So, for instance, the set of rational numbers, which is countable, is dense in the reals, which is uncountable, for example. And we want to use the density of simpler sets to construct our sieves. Okay? So, from the theory of approximating functions, we know that there is a proper subset P of C of polynomials that's dense in C. Okay? So the set of polynomials is smaller and is simpler than the set of continuous functions. Okay? However, it's still in infinite dimension. However, if we limit the degree of the polynomials, we can make it much simpler. So what's going to be our sequence space? So we can start with a polynomial for the 1, and then polynomial for the 2, or for the 3, or for the 4, or for the 5, until we get an approximation to the to the unknown function that will be good enough. Okay? And in the limit, as we have a polynomial that's of order large enough to have a perfect fit to the unknown function. Okay? So when the basis functions are all known, okay, we call them the linear sieves. Okay? The problem is linear in the parameters, and methods like OLS, when j is less than t, ridge, lasso, and all its generalizations, and Bayesian boosting as well, can be applied to estimate these models. Okay, we are going to discuss a bit about ridge on the second block of this lecture. Okay, so for example, let p equal to 1 and pick a polynomial basis. Okay, so what's going to be our approximating function? It will be just a polynomial on x of order j. Okay, like the one we have here. In this case, the dimension d of hd is j plus 1 because we have an intercept here. Okay, so we have beta naught, so that's why we have plus 1 here. Okay. So if j lower than t, then the vector of parameters beta that we have here, beta naught, beta 1, beta 2, beta 3, beta j, okay, can be estimated by ordinary least squares, as simple as that. Okay. If j is large compared to t, then we use penalized estimation. Okay. When the basis functions are also indexed by parameters, then we have what we call the nonlinear sieves. And then nonlinear least squares method should be used. This method is more complicated. Examples like regression trees, neural networks, deep neural networks, things that we are going to study in the upcoming lectures. Okay? And of course, when we move to nonlinearity, overfitting is an issue. We have to avoid with overfitting, so we should be very, very careful when we are specifying these methods. Okay? So how many sieves? Okay? So for linear sieves, the problem is equivalent to variable selection in linear models. So we can use cross-validation information criteria, or we can use regularization, like any selection mechanism like lasso, adaptive lasso is possible. We can use boosting or Bayesian, any of the methods that we studied in our previous lectures. For nonlinear sieves, the problem is way more complicated. Information criteria is not always a good alternative because in several cases it's not available. And why it's not available? Because we don't have an expression, a closed form expression for the degrees of freedom. Okay? And on the other hand, regularization, sort of regularization and boosting are viable alternatives. For instance, in neural networks, we are going to see that regularization plays a very, very important role. Okay? All right, so let's move into a bit more formal definition. So let's assume that we have a model that has a component, a function, that I'm going to call m naught of x plus u. And this function m naught, the true function, can be split into two terms. A parametric component that we are going to consider to be linear. Okay? Why? Because that's the simplest model that we can have. I hope that now I have convinced you that linear models, the linear model is a good model and should be a kind of our starting point, our benchmark. Okay? And then we have this linear model that's going to be fully parametric, and we have our set of parameters beta naught, the true parameters that the parameters that live in the population, okay, plus a non-parametric component h naught, that which we don't know, could be highly nonlinear, okay. Use the random terms. To simplicity, as I mentioned, we are considering p fixed, okay. So this beta naught is finite. It's finite dimension, okay. That's for these first results. We are going to see in the future, in the near future, in some of our upcoming lectures, that we are going to relax that. Okay? And let's assume that the condition expectation of u on x is 0, and the condition of variance does not need to be constant, but it's finite. Okay? So our goal, we want to estimate this vector of parameters theta naught that consists of a finite term, that's beta naught, and an infinite dimension parameter, that's h naught, that's this nonlinear function. Okay, so our parametric space is the Cartesian of a finite dimension compact parameter space B, and the infinite dimension parameter space H. Okay? And what we are going to do basically here, we want to estimate this by simply looking at a minimization of the sum of the squared errors, as we have here on this slide. And what we are going to do, instead of looking for all possible functions, we are going to look at smaller sets, parametric sets, but that will be dense in theta. So as we increase the complexity of the set, so I'm now translating what you have on your slide, instead of searching over very complex function spaces, we are going to search over much simpler function spaces, but of increasing complexity. We allow this function space to get more and more complex in a sequence. Okay? It looks complicated, but look at that example here, just to give you an idea what I'm going to show you. The blue dots are the data. This is a scatter plot of x against f of x. Okay, the y function here. The y. So this is y over x, and we have a very nonlinear form here. So y is 0.2 minus 10 times x, that's a linear component, plus x exponential of x squared plus the error. Okay? So this true function here, here without the e, is the red, the green line, the green curve that you see over the dots. Okay, so that's our target. Note that we don't want to fit all the blue dots. That will be overfitting. What we want a perfect fit over the green line. That's our target. Okay, so what are these increasing complexity spaces? It's like starting with a linear model. That's the much simpler one. So we are trying to approximate the green by a linear function. That's the less complex approximating parameter space. But then we are going to increase in complexity. Now this is a third order polynomial. Much better, right? So the purple is much closer to the green than the yellow. And we go like this. So this is the fifth order. It's much, much better. So we are getting really close to the green function. So we are doing a pretty good approximation. And in some parts we have a kind of almost perfect fit. So that's what I mean by increasing a sequence of sets with increasing complexity. What are my approximating sets? The sets of polynomials. So the first one is the first order polynomial, then the second order polynomial, third order, fourth order, fifth order, so on and so forth. Okay? And then we can go up to the 10th order, and very good fit. So that's the idea. Okay? But it's much easier to look for polynomials to approximate this complicated nonlinear function than try to search over all possible nonlinear functions or all possible nonlinearities to try to find the right one. So when we have no clue of which is the functional form, we can use like these basis functions that when we increase complexity, when we have like a polynomial that has an order that's large enough, a polynomial, this class of mods will be dense in terms of continuous differentiable functions. Okay? So basically that's the idea, and what I'm going to show that we can approximate pretty well the class of Holder functions, the Holder class of functions with linear sieves. And the Holder class of functions are functions that obeys the Holder condition. When we look to the L1 norm of h evaluated at x minus h evaluated at y, this is equal or less than c times the L2 norm of L1 norm, sorry, of x minus y to the power of gamma. Okay, sorry, the L2 norm, the Euclidean norm. So there is a 2 here. Okay? And we denote a p-tuple alpha with non-negative integers, okay, and the set of the sum of these integers, and we denote the differential operator, that's the derivative of order alpha of something, okay, and we want to estimate functions that where the alpha derivative of these functions satisfies the Holder condition. So we want some kind of well-behaved functions, okay? This may look a little bit complicated in terms of math, but the idea is the following. We start with nothing, right? We have data, y and x's. There is a nonlinear relationship between y and x. We are completely clueless about this relationship, okay? So what we are going to do, we are going to approximate this very complicated nonlinear function by some simple blocks, which I can understand, like polynomials, trigonometric functions, okay? But how good are these approximations? Depend on how complicated is the nonlinear function. So if we want to use simple sieves like polynomials or trigonometric functions, we need the unknown function to be restricted to a certain class. Okay? And this function should be smooth enough such that we have the derivatives will satisfy this Holder condition. Okay? And basically we can show that functions that satisfy these Holder conditions, these Holder class conditions, can be well approximated by linear sieves. Which kind of sieves? Polynomials is one kind of sieve. Okay? Note one thing here, that I'm restricting x to be between 0 and 1. This is a normalization. Why is that? Because we have to truncate the data, so we can only approximate this over a compact set. We have nothing to say outside this compact set. Okay. Of course, it doesn't need to be 0 and 1. We can be x belonging between a and b. Okay, but this is without loss of generality. Okay? And there is this theorem, the Stone-Weierstrass theorem, which shows that a polynomial of order large enough, we can make the distance between this unknown function, the continuous unknown function m and p pretty small. Okay? So I have shown you an example 2 slides ago where we use a polynomial to approximate a highly nonlinear function. Okay? So, for instance, we can generalize it when we have like p larger than 1. So this is an example if p equals to 2. What we have the squares and we have also cross products, okay? And for any p larger than 1, what we have is that we're going to have our sieve will be quite complicated because we are going to have all kinds of cross products, okay? But once you define all the cross products, the estimation, the model is linear on the parameters. So we can use standard techniques to recover these betas. Okay? However, note that even if p is less than t, the number of parameters to be estimated could be quite large, right? Because this involves all possible cross products. So even though p may be small, after you take into account all interactions, you may use some kind of regularization to estimate this model. Okay? Another function is the trigonometric polynomials. That motivation for any of you who has a background in engineering, math, or physics, you know about Fourier series, and that's the idea of Fourier series. You are just approximating your nonlinear functions by polynomials. Okay. And let's go back to the example. Let's try to approximate the green line by a trigonometric function. That's with k here. What we are looking is j, right? There's a type in the graph, but we are just increasing the number of polynomials. Okay, one polynomial, two trigonometric functions, 10 trigonometric functions, 20 trigonometric functions, 13 trigonometric functions. Okay? Of course, we approximate like the overall low frequency component, but the trigonometric functions introduce some extra noise because we have this periodic behavior. Okay? So in this case, because this function is not periodic, the function that we want to approximate, the polynomial fit was much better. Okay? When p is larger than 1, there are several ways to generalize trigonometric polynomial. The easiest way is to consider additive separable models. So instead of making a full nonlinear model of all the regressors, you have a nonlinear model of regressor 1 and a nonlinear model of regressor p, and we have these additive terms. Okay? So there is no cross terms. We can also do this for regular polynomials. Okay? Or we can consider tensor products, where we look at all cross products of the variables, or of the trigonometric functions of the variables. Of course, we have special cases like the cosine polynomials or the sine polynomials. So here's the fit for using the cosine. So the cosine is not really good for this specific case. Okay? And why is that? Because it's well suited for periodic functions, but in this case, the cosine was not good. On the other hand, the sine function was much better. So do you have any ideas or things for us to discuss on Friday? Why the sine function is a good function here, but the cosine was not a good function to approximate this specific nonlinear target that we have here. Okay? Something for you to think about. And Finally, we have the spline. So the idea of the spline is like to try to split the space in simpler spaces and look at like piecewise simpler functions. Okay, so let's have our JT and let's define a sequence of integers like from C naught to C JT plus 1. They are real numbers. Okay, sorry, the J is a positive integer, Xi is a real numbers. They are between 0 and 1. Okay, and we are ordering these numbers. Okay, and we are dividing the 0, 1 interval. That's our the support of our function. That's the domain of X. We are going to divide in this. So basically, if we have here X, we are dividing our function here into some regions that will be defined by the Xi's. Okay, and these Xi's are called the knots, and we consider they have the bounded mesh ratio. So basically, they are almost equidistant from each other. So they are not they do not differ much. The interval between two adjacent knots. Okay, and we define a spline of order R with knots Xi1 to Xi_jt. It will be a polynomial of degree R minus 1 or less on each interval. So at each interval, so again we have something here. We have the intervals. Say, we're basically saying, okay, in this interval we have a polynomial, in that interval we have another polynomial, we have another polynomial here, and another one here. And they are of order R minus 1. And by combining these piecewise polynomials, we can recover a much more complex function. Okay, so that's how we define a univariate spline. Okay, it's defined in terms of a polynomial, overall polynomial of order R minus 1 plus for each knot we are adjusting. Okay, also with a polynomial here that will be the max between the point X. Okay, here. The point X, use a capital X, sorry, no, not lowercase x, minus Xij to the power of R minus 1. Okay, so better to see as an example. So here we have this blue function that we want to approximate. So this is no spline at all. We are just like taking piecewise constant models. So we divide into two. We have two knots. Okay, and then we have a constant here, another constant there, and a constant there. Not really good fit. Or we can have a linear function. So we fit a linear function here, another linear function here, and another linear function there. Okay? Or we can do continuous piecewise linear functions that we put the restrictions that there's no discontinuity. Okay? So this is kind of a piecewise linear basis function. But we can do it with cubic splines, where at each sequence, at each part of our domain, we fit a cubic polynomial. So the first one on your up left panel, you have something that's kind of no continuity restriction. On the up right panel, we have the same cubic polynomials but with continuity restrictions. Okay, but still not too smooth, so we can even impose more restrictions, like restrictions on the first derivative. So the bottom left panel, we have a cubic polynomial, but we are imposing that the overall function has continuous first derivative. And the last one, which is kind of the best fit, we are imposing that the second derivative is continuous, okay? So this is an example of splines, and then we have a special case that's called the natural splines, okay? Because the behavior of polynomials fit to data tends to be very erratic near the boundaries, and extrapolation is kind of dangerous. So splines also have this problem, okay? So the polynomials fit beyond the boundary knots have even more kind of widely behavior, okay? And this can be summarized in terms of the variance of the spline functions when it's fit by least squares. So what we want to do, we are going to add additional restrictions, okay, that the function should be linear beyond the boundary knots, okay, and this will free up some kind of degrees of freedom, okay, which can be spent in kind of getting more complex behavior in between the boundary knots, okay. So the idea is that if you have just a global linear model, that's the pointwise variance that you get, okay, over X. If you go to cubic polynomials or cubic splines, you have a variance that is go up, but you have a natural spline, you kind of keep this variance on the boundaries much lower than a cubic spline, okay? And so what the figure represents is the pointwise variance curves for 4 different models with X consisting of 50 points drawn from a uniform random variable between 0 and 1, okay? And the linear and cubic polynomials fits have 2 and 4 degrees of freedom respectively, while the cubic spline and natural cubic spline have 6 degrees of freedom, okay? And the cubic spline will have 2 knots at 0.33, 0.66, while the natural spline has boundary knots at 0.1 and 0.9 and 4 interior knots. So you have much more knots in between, so you can approximate much better your function by restricting the extremes, okay? So how will we do that? So for instance, take something of order 3, that's our expression of our approximating function, okay? Basically what we are going to do is that we are going to include restrictions. Okay? First, that the second derivative of h is equal to 0. The third derivative is equal to 0 for any x that's below the first knot or larger the last knot. So we're imposing linearity. So this basically sets a2 and a3 equals to 0, okay, and sets the sum of b's and psi b's to 0. So we may allow, you may have a larger j here. So we may have more knots because we are freeing some degrees of freedom, okay? So these conditions we can satisfy by setting what we call the natural splines of the function n1 equals to 1, n2 equals to x, and then we define nj plus 2 will be these differences between this function d, and d is defined here, okay? And then we can use these basis functions. So our natural spline, we use these as approximating functions, okay? And that's it, okay? For natural spline. So introducing more flexibility to the model, and of course we can also use smoothing splines where instead of just minimizing the sum of squared errors, we introduce a regularization term that's related to the second derivative of this approximating function. Okay? And of course, we're imposing these on the spline function. Okay? And so our approximating function will be given by a linear function on the ends. And which are the ends? The ends that we are defining here. Okay? Or even more general, this restriction here can be seen as a generalized ridge, okay, where you're estimating theta, okay, like the OLS n transpose n minus 1 n transpose y, but there's a regularization term. But instead of having an identity as we had before with the ridge, what we have is a matrix formed by like the integral of the second derivatives of the function's n. Okay, so that's what behind natural splines and smoothing spline. So let's go to that, our function here. Let's see how a smoothing spline fits that function. So very simple, a equals to 0. That's linear model. 0.3, 0.6, 0.95. You see that among all the approximating functions, it seems that the spline did the best job, right? Okay. We can do multi-dimensional splines by considering tensor products. So looking at the products of two splines, okay, and we can represent our final function as a sum over these tensor products, okay? And we can generalize this for p much larger than 2. Of course, things start to get complicated in large dimensions. We will discuss this more later on, okay? All right, so one-dimensional smoothing splines generalized to higher dimensions. We can use regularization, and the problem is to compute this regularization term, this j, and already for p equals to 2, this involves kind of a double integral that could be a little bit difficult to evaluate, okay? So this is a linear spline. So linear sieves, in my opinion, they work well when you have a finite dimension problem, when the dimension of your axes are pretty small. When the dimension of axes start to get really large, things start to get ugly. So we have to move to nonlinear sieve space. The most famous nonlinear sieve space was what we called artificial neural network, and we are going to have a special lecture just to talk about neural networks. But the idea is that we are going to approximating by this function S, and this function S has its own parameters, these gamma parameters here. So basically we are taking a linear combination of the x's, and then we are passing through a smoothing function called x, that's called the activation function. There are many classes of activation functions, and there are many results in the literature that depend on your choice of x. You basically can approximate not only continuous functions, but you can approximate any Borel measurable function. Okay? So it's very, very flexible, and it scales up beautifully. Okay? It's much easier to use these models when you scale it up, or when the number of regressors is large. Okay? So let's see how a neural network fits the data. This is one term here in the neural network, j equals 1, 3, already pretty good, huh? Much better than any other. 7, if you start to increase too much, then it starts to get some noise, right? So you see that it starts to doing some overfit. But with 3 of these functions, approximating functions, we can recover our green line pretty well. Okay? All right, so what we can say about theory for fixed P, there are many results in terms of consistency. Basically, the papers that you have on your Dropbox, this one here, the authors show that the estimator for your unknown function converges in distribution to a normal random variable. Okay? And basically, you can do inference without much problem. Okay? The issue, and I think that's what matters for us here, is when P is larger than T. Then things start to get way more complicated, okay? And we have to use more complicated methods that we are going to see here. Okay? So that's it for today. For this first block, we have a second block, and on Friday we can discuss more about this material.